Hello, and welcome to my talk about the research into a malicious SDK from Mintegral that we codenamed SourMint. My name is Danny, and I'm the co-founder and chief security officer at Snyk. I have been working in the security industry, specifically in research and the cryptography domains for more than 20 years. I'm also a CTF, a capture the flag player with my team Pastan. And you can find me on Twitter under the Grander handle. I'm just here to share the details of the research, but the folks who did the actual research here are Kirill and Raul, the two researchers who are part of the security labs group at Snyk. So just a little bit about what we do at the Snyk Security Labs. Basically, we do research into open source components, but not only open source. Actually, like you will see in this research, we'll look at all the software components that reside in major package managers. And of course, open source components as well. When we do find security issues and vulnerabilities and malicious components, we do what's called responsible disclosure. Basically, we report the information to the vendors, to the maintainers, let them fix the issue, and then we go public with it. So we also a CVE numbering authority. Basically, we are a CNA. We get to assign new CVE identifiers to vulnerabilities and issues we disclose. We are part of the OS contributing member and Linux Foundation, as well as Node OpenJS Foundation, the security working group there. So just two interesting examples for previous research we did. So ZipSlip is one. You can follow the link here. This is basically a case of a 30 years old vulnerability that still affects a lot of software products, and we found more than 1,000 such vulnerabilities in all the popular applications and projects. And an interesting case we covered was the event stream malicious library, basically a malicious component that was inserted into a library by a malicious actor, an open source maintainer that introduced that code just to be able to eventually steal Bitcoins from an open source Bitcoin wallet. So when we conduct security research, when we do our analysis, basically, we do it at scale. So we look at all the kind of components that we get see on GitHub, the open source component, on the different package managers like NPM and Maven and PyPy. We have Ruby Gems, Composer, Go. So there is a lot of package managers, and some actually deliver open source code, and some deliver just binaries, closed source code. So whenever we do a research, we try to do it at scale. So for example, we try to identify a pattern, a vulnerability, a line of code that can lead to a vulnerability, and basically find all the instances of that pattern in all the components out there. So this is sort of like parsing, throwing a huge net into the ocean, and then grabbing everything that falls into a very specific criteria that we define. And so that's exactly what we did with Cockapods. Cockapods is a package manager, kind of the native package manager for iOS. And so there you can get your open source component, but also some components are just binary components. So when we looked for different components that had some kind of that had something different about them, we identified the Mintegral Ad SDK. And what was different about it is that it had several weird things. One, it would had some obfuscated content, some obfuscated data with a very specific proprietary base 64 decoding. So if you would try to decode it with base 64, you wouldn't get anything meaningful. It used meta swizzling. Basically, it hooked into an system APIs and intercepted the data that was sent to them. So this was definitely not standard behavior. And so when we looked into this SDK deeper, we found quite a lot of interesting things. So before we kind of dig into the details of our findings, let's quickly look at the company itself. So Mintegral It's an online monetization platform. So basically, they help developers monetize on their apps through advertisements that they place inside the apps. So this is the company is owned by Mobvista, which is a public company traded in Hong Kong, and the Mintegral is headquartered in China with offices around the globe. So this is the page, kind of from their website. They offer an SDK that you can integrate as a publisher, as an app developer. You can integrate into your app. You can kind of let it know where you want to when and where you want to display advertisements, and then they will deliver those advertisements and pay you for for any kind of clicks or impressions or whatever that happens from within your app. So looking at the Mintegral SDK itself, it's available for both the Android and the iOS Apple ecosystems. And looking at on August 2020, this SDK was integrated to more than 3,000 applications, and it was downloaded more than 1 billion times a month. So the applications that had the SDK integrated into them in total resulted in more than 1 billion downloads a month. So this thing, what we will show you, we found was operating for at least 1 year. So you can see how huge numbers you get here just by looking at how many consumers were affected by this throughout the year. So since we don't have much time, it's only 25 minutes talk, and absolutely follow the links I'll share in the end to kind of read through all the technical details of this research. But just covering all the findings real quickly here. So on the iOS SDK, we found that it intercepts all the HTTP requests that the application performs. So this would be any HTTP request sent to the backend of the application, right? So they would capture those the URL, the HTTP headers, and report them back to Mintegral with all the additional information about the IDFA, the additional metadata that they could grab and report back to them. They would also intercept all the kind of open URL. So whenever you click on a URL from within the app, they would track it and report them, and as well as StoreKit events. So this is when you open an app store from within the app. Basically, when you click on for example, on an advertisement that advertises an app. So what's important here is that not only this, excessive tracking was performed using a method that is not acceptable in this context, which is method sweetening. Basically, you intercept, you dynamically instrument yourself into every API call, in this example for HTTP request, and you get the data, you get the information, you can just grab it and send it to your servers. So this was one, but also it was hidden. It was obfuscated with different, the base64 encoding I mentioned, which is not the standard base64 encoded. It's a mangled version of the base64 encoded. And this, when you looked at the code and the binary, you wouldn't immediately see anything suspicious. But and so one other very important thing is that this functionality, the tracking functionalities, was always enabled, even if you chose not to enable the SDK in your app, but you just integrated it. You just not integrated. You just placed it inside your app. This is my 2-year-old baby crying there in the background. Hope that's not a big issue here. So when you integrate the app when you integrate the SDK into your app. And even if you didn't enable it, if you didn't, let it present ads, or the mediation platform SDK didn't let it present ads, it would still track all the HTTP requests, all the URLs, all the stuff. So that's the other thing. And then finally, it tried to avoid detection. So they would look for attempts to debug the application, dynamically debug the application. So they would kind of turn off all the bad functionalities. If the device is jailbroken, they wouldn't do all their stuff, because this kind of there is more potential to for the discovery of this functionality when you operate on a jailbroken device. And finally, they also identify whether you try to intercept the traffic. So again, when you try to investigate what's going on, they would hide everything. So they did so successfully for more than a year. So just in one example, and this is just a theoretical phone editing app. I'm not mentioning any real world apps here because there are plenty of very, very popular apps, and I wouldn't want to hurt their business. They are just folks that integrated the SDK without knowing that it does all the bad things that it does. But this, we did find it in, as I said, in the most popular games you all heard of, but also on one of the most popular photo editing apps. So just an example, that photo editing app was sending authorization header authentication token to their servers to authenticate the user. So that authorization token would be sent also to Mintegral because this is part of what appears in the HTTP header. So that would be intercepted and sent to their server. Just one example. What we also noticed is that basically, with all this data they're collecting, they are performing what's called an advertisement attribution fraud by performing clickjacking. Clickjacking is an attack where you send a fake click right after the legitimate click. So, suppose the user clicks on an advertisement, Mintegral gets this data, they see this, and so they send a fake click immediately to the mobile measurement platform, to the mobile measurement provider. And so when that app is being downloaded and then opened, the MMP, the mobile measurement provider, needs to decide who gets the attribution for that installation, who gets the paid for that installation. And so the way they operate is they choose the last click. So in this case, if this was the fake click, they would attribute, coming from Mintegral, they would attribute it to Mintegral, and Mintegral would get paid for this, stealing the revenue from the legitimate network in this case. So this is a quick video just demonstrating this excessive data collection functionality on iOS SDK.
In this short video, we'll demonstrate the SourMint malicious SDK, which was distributed as a legitimate ad SDK by the Chinese company Mintegral. In August 2020, Snyk identified that the Mintegral SDK performs malicious activities like advertisement attribution fraud and leaking sensitive data. This video demonstrates the latter. The SDK is distributed as a legitimate ad attribution SDK, but it holds malicious functionality, hence the name SourMint. The malicious SDK at the time of recording affects over 1,200 applications available on Apple's App Store, which has been downloaded over 300 million times every month. On the right hand side here, we're running the Charles debugging proxy, which is connected to a live mobile device running an application we created that uses the malicious Mintegral SDK. This malicious library detects when proxies are connected and will not behave maliciously if monitored. However, we're going to set a couple of flags on responses sent back from the Mintegral servers to our mobile application so that the responses appear direct. We'll start the application on our device and show you the market-disrupting application called ScanQR. Oh yes, QR codes are still a thing. In the background, you can see some requests sent from the Mintegral SDK in our application to what appears to be a legitimate settings.rayjump.com URL also owned by Mintegral. When the responses come back from the settings endpoint, we set flags upon them so that the Mintegral SDK running on the app believes it's not being monitored. Back to the ScanQR app. We're going to scan a QR code that contains the URL to a top secret document of ours. Please don't tell anyone about this. It's top secret. When we head back to the ScanQR app, the Mintegral SDK is able to get back on the CPU of our device and makes a request to the malicious n.systemlog.me URL. Digging deeper, we can see an encoded payload is sent. We'll copy this to the clipboard and in our terminal on the left, pipe the malicious payload into our script so we can decode it. In the output of our script, you can see the original encoded malicious payload followed by the decoded payload. There's a second layer of encoding used in the field named clever, which we further decode to reveal a JSON payload, which includes the URL of an HTTP request we made from our application. Mintegral now have access to our top secret document. The malicious Mintegral SDK is monitoring every single HTTP request our mobile application makes and sending back potentially sensitive data about both the application and the user. Visit the Snyk.io research site for more information about this malicious Mintegral SDK and SourMint.
So on August 24th, we published all our research after disclosing this to Apple, and so and also to various big publishers of mobile applications. So on 24th we went public. We posted a blog post, and this was covered by many different outlets. So and a day later, Mintegral posted their response, basically denying all allegation here. And so what happened is that one interesting tweet appeared right after our publication, and this is the beauty of the community and the research community, is that when you share something with the world, people see it, people can look for themselves and try to do their own research. And so what we've seen is somebody posting this tweet saying that they identified some really interesting and suspicious parts of the SDK on Android. So that's when we decided to check again. So we went back to look at the Android code, which we didn't find anything before. We already published our iOS findings, and we kind of were ready to move on. And then we find some more interesting things with Android. So specifically, we found a hidden, again, very similar obfuscation, just like in iOS, a hidden component that was performing download tracking. So they would intercept all the intents of download URIs from Google and report them back to their own servers. So this was, if you would go to Google Play Store and install an app, they would get all the information about this app. We don't know what they did with the app, but with the data. But one thing that is very easy to do in this case is just send a fake click, right? Like this time attributing an install from organic install to an advertised install, right? So while we didn't confirm this is there is it's hard to imagine any other reasons kind of to capture this data. But anyway, this is what the SDK did. But also, interestingly, they captured all the downloads coming from Google. So for example, not only Play Store. So for example, if you would open, I would send you my secret Google document or my secret Google spreadsheet with all the financial data, and you would click on this URL would also be sent to Mintegral. And the crazy thing is that because, in this case, in Android, this is a global interception of the intent. So basically, you don't even need to be inside the app. You don't need to play that game for them to get the data on all the Google downloads from Drive, from Google Docs that you perform. So again, this was just like in iOS, obfuscated code that using their own kind of encoding schemes to hide from. So this is a short video demonstrating the Android download tracking functionalities.
In this short video, we'll demonstrate how the malicious SourMint SDK leaks sensitive user information on the Android platform. In August 2020, Snyk identified that the Mintegral SDK performs ad fraud and leaking sensitive information on the iOS platform. On the right-hand side, we're running an emulated Android device that is connected to a proxy on the left-hand side. This proxy inspects traffic that our emulated device sends out. We'll navigate to Mintegral's own Android demo application to open up and view a native ad. With this ad banner open, let's navigate now to the Google Drive app on our device and download our secret Google Sheet document. This contains a bunch of my secret data, and I don't want anyone to see it. As soon as we do this, the Mintegral app registers a download event from a google.com URL or application and sends a request to its own server. Notice that this time the request is being sent to a different Mintegral server, namely n.systemlog.me. This is very similar to the behavior we identified back in August with the Mintegral SDK on an iOS application. Digging deeper, we can see an encoded payload is sent. In our terminal on the right, you will use our own script to decode the payload, and you can see that both the file name and even the link to our secret Google Sheet has been sent to the malicious Mintegral server. As a malicious actor, I might go ahead and click on this link to download the secret file and steal the data from the unsuspecting mobile user. Visit the Snyk.io research site for more information about this malicious Mintegral SDK and SourMint attack.
So on September 4th, Mobvista mediation platform, this is Twitter, and IronSource mediation platforms announced the certification and the removal of Mintegral from their platform. And so that same day, Mintegral announced that they have plans to open source their SDK. So open sourcing the SDK. So, they open sourced the SDK, but it wasn't available for anyone that is not their partner or their customer, right? So they did provide the SDK to one of their to many of their customers, but that one of those big publishers shared the SDK with us, so we could perform our analysis. And what we did is a differential analysis. Basically, we compared versions. So we started with comparing version 6.4, which is closed source, with version 6.5 that was released immediately after our publication. So this version was released, I think, several days after our publication. So what we've seen is that one component was removed from it, and this was the open operation PK tasks, which was like very interesting name that is, that does not jump like anything bad. And so they removed it, and that was exactly all the kind of things that we flagged in our publication. All the tracking, all the hidden functionality, all the proxy detection, all that part were removed. So that was great sign. But then we compared version 6.5, the closed source version, to the 6.6 version, which had open source available. And so just one note on how do you do binary to source code analysis. When you compare two source codes, it's easy. You just kind of do a textual diff. When you can compare two binaries, you can do a binary diff. But when you compare closed source to open source, what you can do is compare the symbols, basically the function names that reside in one thing and you were removed or added on the other release. So that's what we did. And interestingly, we identified that there was another piece of code that was removed from version 6.5 and was not included in 6.6, the open source version. And we didn't know about this model. We haven't identified it in our previous result. It wasn't flagged when we threw our wide net, right? Like we didn't identify this component until they published the open source code, right? So this is very interesting. So as you can see from the name, MTG probably stands for Mintegral, remote command parser. So remote command. So let's look at what is this. Basically, what we found is a backdoor. It's a backdoor that allows for JavaScript that being delivered, sent by Mintegral to the mobile phone, to the mobile application, to execute, to invoke any native static function from within the app. This is a very, very big deal. Dynamically invoking from JavaScript by Mintegral any function on my device in my game is a very, very big deal. First of all, it lets them do anything with my app, with my data, with my phone. Like this is the worst that can happen when it comes to letting someone manipulate the code, right? Second, Apple is not involved in reviewing this. Basically, they are bypassing Apple's review here because they hidden a little backdoor that allows them to execute any code that they choose to without running through Apple's review process. So, they delivered the app, they delivered the SDK. SDK is integrated into several thousands of applications. Those applications were downloaded and installed by billions of users, and now they can deliver a little JavaScript code that can run any code of they wish on the device. So this was basically the discovery of the backdoor that allows for remote command execution, RCE. And just to kind of illustrate how this works, so Mintegral would be able to send a banner. We're talking about advertisements here. So an ad would be sent with some specific JavaScript code that you need to know how to trigger. It's not just regular JavaScript. You need to use those encodings and encode, and you need to know what endpoint to call, the MV semicolon / There's a lot of technical details you need to know how to do. But as soon as you know how to do it, you can deliver this code that would execute any code on the device. And what's more important here is that not only Mintegral can do that, any advertiser can deliver such an advertisement, right? So this is much bigger exposure than just Mintegral doing that. So on October 2nd, Snyk responsibly discloses the RC findings to Apple. Apple, like 1 day later, Apple notifies all affected publishers that about this thing and asking them to remove the MTG command parser, MTG invocation boxing code classes from their apps, that those classes that allow for the RC. And so let's look on a short video. Let's watch for a short video demonstrating the iOS backdoor.
Hey there. In this video, we'll show a demonstration of the remote code execution capability found in the MTG invocation boxing class provided by the Mintegral SDK. During this video, we'll be using an application running on a real iOS device that uses the Mintegral Ad SDK. The app will be blurred for privacy reasons. The malicious payload that we will execute can either come from the Mintegral server or the advertising banner itself. We'll be using an ngrok URL to replace the Mintegral server by exposing our own local server to the internet. We spin up our own HTTP server to serve the malicious ad banner running in the app on the device. As soon as the game loads our own malicious banner at the bottom of this app, we can see the IDFA of the device has been sent to our server logs. It looks like this banner is doing some nasty things. We'll take a break from the app to look at some sensitive information, such as this password manager. I'm going to copy the password as I want to use it later, but with this sensitive information in my clipboard, let's head back to the game. As soon as we open it, the malicious ad banner uses the remote code execution inside the Mintegral SDK to run malicious code that steals the password data from the clipboard and sends it back to our evil server. To find out more about SourMint, visit the Snyk research site for more information. Thanks for watching and stay secure.
Cool. And so on October 15th, that's a little less than 1 week ago, we published all our findings, additional findings on the iOS backdoor and the new Android findings on our blog post, along with detailed technical research write-up that we're having all the technical details of this research. So, looking back at this research, which started as, identifying one single iOS component, then with the open sourcing and doing the diff analysis, and then kind of identifying more the backdoor and then the Android code as well, the download tracking. So this became quite a long research project. And, looking back, we're very pleased with the impact here. First of all, malicious code was removed. We have components now that do not hold this malicious code. So on iOS, we had HTTP request tracking, open URL tracking components, iOS StoreKit tracking, and of course the backdoor, the native code invocation backdoor. All this gone, removed. This is immediately after our publication. Second is the Android part, Google download tracking. So all the tracking that was conducted on your Google application installs and spreadsheets and whatnot stopped. The code is out from the Google Android SDK. Second thing, the clickjacking, the advertisement attribution fraud stopped. So this is some data shared by Singular, an MMP that shows before and after the publication. So this is the rates of double clicks, fake clicks, two networks reporting on a click for the same campaign from the same app. These are the rates, and then right after the publication, it's all went less than 1%, right? So this is a huge impact. And finally, we have the SDK open source, right? So while sadly, at the moment, this is available only to their partners. It's not truly open source and available to anyone, in the world to analyze. But this is definitely a step towards, more transparency and openness. And finally, is the increased awareness. So we talked with many publishers, many game developers, and they were all not aware that this was happening. They didn't sign up for that. They integrated an SDK, trying to monetize on their apps through advertisement. But they ended up, spying on their users and, sharing more data than needed with Mintegral, with that company. And so this is, they really understood, the significance of just integrated components that they do not know into their code. So we worked with Google teams and Apple. So all took this very seriously. And so I really feel like how the awareness in the ecosystem, in the mobile ecosystem, has risen. And so in conclusion, we've seen just one SDK that was integrated into thousands of apps, like 3,500 apps. But then these 3,500 apps get downloaded by billions of users. So we know that there are more than billion back in August, it was more than billion users downloading those apps that have the SDK in a month. Billion users in a month. That's a lot. So we can just see how, a choice that we as a developer make in integrating a software component into our code can directly affect billion users. And if we don't know what this component does, and what other components this library, this component presents, then we have a problem. And the solution to this problem is just taking ownership, understanding what we are integrating into our app, what this component does, what other components this brings in, and basically treating them as our own, right? Taking full responsibility for this. So some more resources. We have the initial disclosure that published back in August. Then we have the additional findings around Android and the iOS RC. The full technical research paper write-up that has all the technical details. And finally, a very interesting talk given by Guy Pajarni, my partner at Snyk. He gave a talk about named the developers as malware distribution vehicle. So in this talk, he presented different interesting cases where developers were used to distribute malware. And so I think this is very much relevant to what we've seen here, and I think you all will enjoy this talk. And with that, I want to thank you all for listening. I hope you enjoyed this talk, and stay secure.